Assalamualaikum to Dr. Rose and everyone. Today, I would like to present about the inflation rate in Malaysia from the year 2006 until 2025. First, inflation refers to the percentage increase in the general price level of goods and services over a period of time. In simple words, inflation means the price level of goods and services become more expensive. Inflation is also considered an important economic indicator because it reflects the economic trends and financial stability of a country. Inflation rate is calculated using the Consumer Price Index or CPI with the following formula. Next, CPI stands for Consumer Price Index. It is used to measure the changes in the price of goods and services over time. CPI is important because it helps determine the inflation rate in a country. Understanding inflation is very important because it helps government plan economic policies and allows businesses to make better financial decisions. It is also help individuals manage their wages, savings, investment, and future expenses more effectively. For this study, analysis focuses on Malaysia's inflation rates from 2006 until 2025. The data used in this study were obtained from the Department of Statistics Malaysia, DOSM, for the period 2006 until 2025. The objective of this study is to investigate the trend of Malaysia's inflation rates by using least squares approximation methods. Linear, quadratic, and cubic model are developed to determine which the best curve to represent the inflation rates data. The accuracy of each model is then compared based on their error magnitudes in order to identify the best suitable model for approximating the inflation trend over the selected period.
Okay, Assalamualaikum. So now I will explain the implementation of the linear least squares model for Malaysia's inflation rate data from 2006 until 2025. So the linear model used in this study is expressed as y equal to a plus bx, where a and b are unknown coefficients to be determined. So on the left side, the matrix is constructed using the year data. The first column consists of ones, and the second column contains the value of x, which are the years, which represent the linear term. So on the right side is the vector y, which contains the observed inflation rate values. These matrices form the basis for constructing the least squares normal equation used to determine the best fit linear curve. Okay, so in this slide, the transpose matrix denoted by MT is obtained from matrix M by converting its rows into columns. This step is important because the least squares method uses the normal equation MTM times V equal MT times Y. So next, MT is multiplied by M to obtain the matrix MTM. So this matrix forms the left-hand side of the normal equation and provides the coefficients needed to determine the unknown vector v. So the normal equation is a key part of the least squares method as it minimizes the sum of squared errors between the observed inflation rates and the values predicted by the linear model. Okay, so next in this slide, the vector MTY is calculated by multiplying the transpose matrix MT with the observed data vector Y. So the resulting vector forms the right-hand side of the normal equation. After obtaining both MTM and MTY, the normal system can be written as MTM times V equal MT times Y. So the augmented matrix equation shown below represents the complete system of equations used to solve for the unknown coefficients A and B. So by solving this system, the values of these coefficients can be determined, producing the linear least squares model that best fits the inflation rate data. Next, the least squares solution is obtained using the inverse matrix approach. The coefficient vector is calculated using the equation V equals M transpose M inverse times M transpose Y. So first, the inverse of the matrix M transpose M is computed, and then it is multiplied by the vector M transpose Y to obtain the coefficient vector V. The resulting coefficient values are A equals 144.6437 and B equals negative 0.0706989. So by substituting these coefficients into the linear equation, the final best fit linear curve is obtained, which is y equals 144.6437 minus 0.0706989x. This equation represents the linear approximation for Malaysia's inflation rate data and describes the best fitting curve using the least squares method. Next, in this slide, the error vector is determined using the difference between the observed values and the predicted values from the linear model. It is defined as E equals Y minus MV, where Y represents the observed data and MV represents the value generated by the model. The residuals obtained from this calculation represents the gap between the actual inflation rates and the predicted inflation rates for each year. A positive residual means the actual value is higher than the predicted value, while a negative residual means the predicted value is higher than the actual value. These residuals are useful in assessing how well the linear model fits the observed data, as they provide insight into the accuracy of the predictions. So for the final slide of the linear model, the magnitude of the error vector is calculated. The error magnitude obtained for the linear model is 5.8411. So a smaller error magnitude indicates a better approximation to the observed data. The graph on the left shows the linear best fit curve obtained from the least square method. The curve represents the overall trend of the value data over the selected areas. Meanwhile, the graph on the right shows the residual plot. The residuals are distributed above and below zero, indicating the differences between the observed and predicted values. However, several noticeable deviations can still be observed, suggesting that the linear model does not perfectly capture all variations in the data.
Assalamualaikum. Now, I will explain the implementation of quadratic least squares model for Malaysia's inflation rate data from 2006 until 2025. The quadratic model used in this study is expressed as y equal to a plus bx plus cx squared, where a, b, and c are unknown coefficients to be determined. On the left side, the matrix M is constructed using the year data. The first column consists of ones, the second column contains the value of x, which are the years, and the third column contains the squared values of the years, which represent the quadratic term. On the right side is the vector y, which contains the observed inflation rate values. These matrices form the basis for constructing the least square normal equation used to determine the best fit quadratic curve. In this slide, the transpose matrix, which MT, is first obtained from matrix M. The transpose operation changes the rows of matrix M into columns. This step is necessary in the least square method because the normal equation is based on the product of MTM dot V equal to MT dot Y. Next, the matrix multiplication between MT and M is performed to produce the matrix MTM. The matrix forms the left-hand side of the normal equation and contains the coefficient required to solve for the unknown vector V. The normal equation is the fundamental equation of the least square method. because it minimizes the sum of squared errors between the observed data and predicted values. In this slide, the vector MT.y is calculated by multiplying the transpose matrix MT with the observed data vector y. The resulting vector forms the right-hand side of the normal equation. After obtaining both MTM and MTY, the normal system can now be written as MTM.v equal to MTY. The expanded matrix equation shown below represented the complete system of equations used to solve for the unknown coefficient A, B, and C. Solving the system will produce the coefficient for the quadratic least square model. The least square solution is obtained using the inverse metric approach. The coefficient vector is calculated using the equation V equal to MTM inverse dot MTY. First, the inverse of the matrix MTM is computed. Then, it is multiplied with the vector MTY to obtain the coefficient vector V. The resulting values of the coefficient are A equal to 30258.6945, B equal to negative 29.9534, and C equal to 0.007413. Substituting this coefficient into the quadratic equation produces the final quadratic best fit curve, which y equal to 30258.6945 minus 29.9534x plus 0.007413x squared. The equation represents the quadratic approximation for Malaysia's inflation rate data. In this slide, the error vector is calculated. The error vector is represented by E equal to y minus mv, where y represents the observed data and mv represents the predicted value generated from the quadratic model. The resulting residual value shows the difference between the actual inflation rates and the predicted inflation rates for each year. Positive residual values indicate that the actual value is higher than predicted value, while negative residual values indicates that the predicted value is higher than the actual value. These residuals are important because they help evaluate the accuracy of the fitted model. In this final slide of quadratic model, the magnitude of the error vector is calculated. The error magnitude obtained for the quadratic model is 5.7579. A smaller error magnitude indicates a better approximation to the observed data. The graph on the left shows the quadratic best fit curve obtained from the least square method. The curve represents the overall trend of Malaysia's inflation rate data over the selected years. Meanwhile, the graph on the right shows the residual plot. The residuals are distributed above and below zero, indicating the differences between the observed and predicted values. However, several noticeable deviations can be still observed, suggesting that the quadratic model does not perfectly capture all variation in the data.
Assalamualaikum everyone. Today I'll be walking through the implementation of a cubic least square regression model. Our goal is to fit a smooth third-degree polynomial curve to a dataset spanning 20 years from 2006 to 2025. As you can see on the screen, our structural equation is y equals to a plus bx plus cx squared plus dx cubed. To solve for our unknown coefficients a, b, c, and d, we map our data into a matrix framework. The large matrix on the left is our design matrix, denoted as M. The first column represents our intercept, followed by the columns for our independent variables, x, x squared, and x cubed. On the far right is the vector y, which contains our actual historical observations. We have 20 equations, but only 4 unknowns. This system is overdetermined and cannot be solved directly. We need a way to find the absolute best approximation. To do that, we must compress this massive system into a solvable format using the normal equation. This brings us to the fundamental equation of the least square method, which is the product of M transpose M times V equals to M transpose Y. In this step, we are focusing on the left side of that equation by calculating M transpose M. We take the transpose of our design matrix, turning its columns into rows, and multiply it by the original matrix M. This algebraic operation elegantly condenses our massive 20 times 4 dataset into a compact, symmetric 4 times 4 matrix. For instance, the top left entry is 20, which simply represents our total number of data points or years. Now that we have processed the left side of our equation, let's calculate the right side. Next, we compute M transpose Y by multiplying the transpose of our design matrix by our observation vector. This collapses our 20 unique data points into a single 4 times 1 column vector, representing the weighted sums of our observations. Look at the bottom of the slide. When we bring M transpose M and M transpose Y together, the matrix abstraction disappears, leaving us with a classic solvable system of 4 linear equations with 4 variables. Every piece of data from our 20-year timeline is now perfectly encoded within these 4 lines. With our system of equations fully established, we can now isolate and solve for our coefficients. To isolate our parameter vector v, we must multiply both sides of our system by the inverse of our 4x4 matrix. On the left, you see that the exact fractional representation of this inverse matrix, which guarantees absolute numerical precision. When we multiply this inverse by our M transpose Y vector, we get our definitive solution vector V. These 4 values are our magic numbers: our intercept A, our linear slope B, our quadratic curvature C, and our cubic twist D. Placed together, they give us our final best fit cubic mathematical model, displayed at the bottom, which is y equals to 425,872.4540 minus 618.8164x plus 0.2996x squared minus 0.00004832x cubed. While mathematically sound, a vital final step in any data modeling process is evaluating our errors. Finally, we compute our residual error vector using the formula E equals to y minus mv. To do this, we project our newly found cubic equation back onto our original timeline. We multiply our design matrix M by our solution vector V to generate the model's predictions for each year. We then subtract this prediction from our actual historical data points y. The resulting column vector on the far right shows that the exact margin of error for each specific year. Because we use the least square method, linear algebra mathematically guarantees that the sum of the squares of these individual errors is the absolute lowest possible value achievable by any cubic curve. Our model is optimized, complete, and fully validated. To conclude, we look at our final evaluation metrics and visual models. At the top, we have calculated the magnitude of the error vector, denoted as the Euclidean norm. By taking the square root of the sum of our squared individual errors, we compress our system's total deviation into a single value of 5.7578. This low number proves our model sits incredibly close to the true data. On the left, our graph of the best fit curve maps our final cubic function over time. It beautifully smooths out historical fluctuations, capturing the steep descent and the subtle structural plateau during the mid-2010s. Finally, the graph of residual plots of each year's individual error against a zero baseline. In an optimized regression, these points scattered randomly above and below the zero line. This random distribution mathematically confirms that our cubic model successfully extracted all meaningful trends, leaving behind nothing but unavoidable random noise. Thank you.
Based on the error magnitude obtained, the cubic model is the best fit model because it has the smallest error. The difference between cubic and quadratic only 0.0001. This indicates that both models perform almost equally well in fitting the data. However, based on the minimum error criterion, the cubic model is still selected as the best fit model. The results suggest that increasing the model complexity slightly improves the accuracy of the prediction.